Hello EOS 110. This video is to help you a little bit more in understanding wind-driven currents. In class, we looked at this map of major current systems in the world's oceans. And these currents are all driven by the wind. This is different from the deep overturning circulation or thermohaline circulation that we also discussed in class. You can see here we have these gyre circulations. Gyres are basin scale, roughly circular systems of currents. And we have subtropical gyres, I've labeled STG, here in the northern hemisphere, in the North Atlantic and the North Pacific. And we have subtropical gyres in the southern hemisphere, in the South Atlantic, in the South Pacific, and in the Indian Ocean. There are subpolar gyres, labeled here SPG. There's one here in the North Atlantic and another in the North Pacific. And there's also labeled here the Antarctic Circumpolar Current. This moves this direction around Antarctica in the Southern Ocean. And although not exactly a gyre, this current is driven by all the same processes. So as I mentioned before, these current systems are driven by winds. And so a first step then is understanding which winds are important in which of these current systems. In class, we looked at this diagram of surface winds. We see the 6 bands of winds, 3 in each hemisphere. Now, gyres are driven by 2 bands of winds. You need to choose 2. So the subtropical gyres are driven by the trade winds and the westerlies, both in the northern hemisphere, and the trade winds and the westerlies here in the southern hemisphere. The subpolar gyre is driven by the westerlies and the polar easterlies in the northern hemisphere. The southern hemisphere is a bit different. Here the polar easterlies mainly blow over the land, the continent of Antarctica. So here we have a situation where we have the westerlies blowing over water, and then we have a land mass right next to it. And that situation is what drives the Antarctic Circumpolar Current. In your lab manual, you will find in the practice problem section a practice problem having to do with the subtropical gyre in the northern hemisphere, and you'll see an answer written out for that. So instead of going through that one, I'm going to focus instead on the subpolar gyre in the northern hemisphere as an example. So the wind bands that are important in affecting the subpolar gyre in the northern hemisphere are the westerlies and the polar easterlies. All right, so our first step always in thinking about these currents is to identify which wind bands are important. We're going to talk today about the subpolar gyre in the northern hemisphere. And the important winds are the polar easterlies and the westerlies. When the wind blows on the surface of the ocean, it causes the ocean to move, but only about the top 50 meters of the ocean is driven directly by the winds. And that layer we call the Ekman layer. So the first step, the next step after we have determined which winds we need to think about is to think about which direction that Ekman layer goes. So I'm going to draw a picture here showing the winds. So these are my polar easterlies. And this type of arrow indicates wind. And here I will put my westerlies. We learned in class that the Ekman layer always moves 90 degrees to the direction of the wind, but which direction it moves depends on which hemisphere, because the reason it turns is because of the Coriolis force. So we've learned that the Coriolis force tends to deflect movement to the right in the northern hemisphere and to the left in the southern hemisphere. In this example, we're looking at the northern hemisphere, so we'll be thinking of the Ekman layer moving to the right of the winds. I always think it's a good idea to turn your piece of paper so that you look directly along the direction that the wind is going, so the arrow points away from you. And then it's easy to see which direction is to the right. So my Ekman layer will move 90 degrees to the right of the wind. Now I'm going to turn my piece of paper around so that I can look again along the direction of the winds for the polar easterlies. And my Ekman layer still moves 90 degrees to the right. So these thick arrows that I've drawn here indicate the Ekman layer or Ekman transport. Now the next step we want to think about is whether the water is coming together in the center of this gyre or pulling away. In the subpolar gyres, we can see that the water is moving away from the center, right? This water is kind of pulling away here. And so we have what we call divergence at the center of this gyre. The sea level here in the center is literally lower than the sea level around the outside. And that difference in sea level is what drives the major current systems that we were looking at in our map before. To understand which direction the current will be driven, we make another little diagram. We're going to show our low sea level in the center of our gyre and higher sea level around the outside. This difference in sea level is maybe on the order of ½ a meter, so not very large, but very significant in terms of its effect on ocean currents. Now we're ready to figure out what direction these currents are going to go. When we have a situation with high sea level and low sea level, the water at the high sea level wants to rush towards the low sea level. We call that the pressure gradient force. You're welcome to also think of it just as gravity, right? Things want to go downhill. However, the water won't be able to rush directly downhill because, again, the Coriolis force is going to divert it, and it will do that to the right of the direction of original motion because, again, we're in the northern hemisphere here. So the way I do this is I again line up my piece of paper, so I'm looking from the high towards the low. I start out drawing an arrow as though I'm going to draw it straight from the high to the low, and then I turn it in the direction that the Coriolis force is going to deflect it to the right in this case, because we were doing this for the northern hemisphere. Again, I'm going to start out going from right to low and then turn my arrow, going from high towards low, and then I turn my arrow to the right. Now we can see the direction of the currents. Instead of the water rushing into the center, it will be deflected and it will have to go around the gyre, and the direction of that is going to be counterclockwise following the arrowheads. So these subpolar gyres, we've been able to determine here, just based on the direction of the winds, that we expect the currents to move in a counterclockwise way. The gyre circulation also has a profound effect on biological productivity. In the case here of divergence, we're causing essentially an upwelling in the center of the gyre. If I draw this gyre in cross-section, right, so here's the low part in the center, and here's the high on either end. We learned the Ekman layer was moving water away from the center. Right, water is moving away from the center, and so this causes an upwelling of deeper water from below. Remember that the deeper water has higher nutrient concentrations in it, and so as this nutrient-rich water is brought to the surface by this, we can generate higher biological productivity in the center. So these subpolar gyres are marked by divergence, which creates upwelling, and higher biological productivity. Okay, so that's an example that we've gone through here for the subpolar gyre in the Northern Hemisphere. I encourage you to think about going through a similar sequence of steps to understand the subtropical gyres in both hemispheres and to think about the Antarctic circumpolar current.